Thank you very much. I'd like to thank the organizers for inviting me to speak at this meeting. It's a real honor for me to do so. I'm going to tell you about the flow of electrons in certain metallic systems, which is more like the flow of a fluid like water through a pipe, rather than the flow of electrons in more conventional metallic systems like metallic wires. For some reason, the title of my talk seems to have got chopped off on this slide. The full title is Electron Hydrodynamics when electrons in a wire flow like water through a pipe. So just to set the stage for what I'm going to be talking about, so let's just consider these two kinds of flows. So the flow of electrons through a conventional metallic wire and the flow of water through a hollow pipe. So there are, of course, superficial similarities between these two kinds of flow. So both of them involve setting up a steady current due to a gradient of something. And in the case of the metallic wire, the gradient, of course, is a gradient of the voltage. In the case of water through a pipe, it's a gradient of pressure. And the current which is set up is, of course, of different things. So in the case of a wire, it's a current of electrons. And in the case of the pipe, it's a current of water droplets. So these are the similarities. You have a steady current which is set up by the gradient of something. But then what are the differences? And so there are, of course, differences. So as I said, one difference is the quantity in which you're setting up the gradient, voltage in one case and pressure in the other case. It also turns out that the relationship between the current density and the gradient is a little different in the two cases. In both cases, it's a linear relationship. There's a constant of proportionality. In the case of electrons flowing through a wire, it's the familiar Ohm's law. And this constant of proportionality is the electrical conductivity. And this is an intrinsic property of the material that the wire is made of. Now, in the other case, there is a similar linear relationship between the current density and the pressure gradient, except that it turns out that the constant of proportionality is not really intrinsic. It actually depends on the dimensions of the pipe, in particular the radius of the pipe is proportional to the square of the radius. And the other quantities are intrinsic to the fluid that's flowing, water in this case. So those are the differences. And you can ask, well, why do you have these differences? And it turns out that the differences arise because of the microscopics of the flow, or more specifically, the way in which the particles which are flowing are actually interacting with one another and with other things. So when it comes to electrons flowing through a wire, it turns out that the momentum of the electrons is actually not conserved in the bulk. So as the electrons are flowing through the wire, because the wire is made of some material, the electrons actually interact with the material. And it turns out that the momentum of the electrons is taken up by either the vibrations of the ions that make up the metal, what are called phonons, or by impurities that can exist. So these can act as sinks for the momentum of the electrons. The electrons, of course, are colliding with one another, but that collision conserves momentum. So that is not a momentum sink. On the other hand, if you look at water flowing through a pipe, then because the pipe is hollow, there isn't anything inside, you only have collisions among the fluid droplets in the bulk, and there is no momentum loss. They just exchange momentum among one another, but there is no momentum loss of the fluid. And so that sort of turns out to be the main reason that the flow is different in the two cases. The other big difference is that if you look at the velocity profile, if you look at the velocity of the fluid as you go along the cross section of the wire in this case and the pipe in this case, in the first case, when you have electrons flowing through a wire, that velocity is essentially constant. Whereas if you look at a fluid flowing through a pipe, there's a gradient in the velocity with the layer of the fluid in contact with the surface of the pipe, essentially stationary. And then the velocity increases as you get to the center of the pipe and then decreases again. So there's also a difference in the velocity profile, which ultimately arises because of this issue of momentum conservation in the bulk in this case and not in that case. Okay. So you can ask the question, if not for any other reason, just for intellectual curiosity, is there any practical situation in which you can actually get electrons in some kind of a metal to flow the way that a fluid flows through a pipe? And so, of course, you can think about it, you can idealize the situation, but in a practical situation, it turns out that it has to do with length scales. And so if you're looking at electrons which are flowing through a wire, then there are different regimes of flow that are possible depending on what the operative length scales are. And so if you have a situation in which you have these electrons bouncing off impurities or of these lattice vibrations, then that is sort of the conventional situation in which you get Ohm's law, and which is also called diffusive flow. And the operative length scale in that case is this L diff, which is the mean distance for the scattering of the electrons of phonons or impurities. Now, you can also have a situation, which I'm not really going to be talking about, in which the electrons that are flowing through the wire are mainly bouncing off irregularities in the walls of the wire, something that's called ballistic or Knudsen flow. And it turns out that the operative length scale in such a situation is the radius of the wire. And then finally, if you want electrons to flow as water does through a pipe, it turns out that the operative length scale is this length scale LEE, which is the mean distance between electron-electron scattering events, the mean distance that an electron travels before it collides with another electron. Now, in any situation, all of these length scales are present, but as I said, the important thing is which one is the operative length scale, or which one is actually the smallest length scale in the problem. So if you can somehow engineer a situation in which this particular length scale, the length scale that has to do with how much the electron travels before colliding with another electron, is much smaller than the other two length scales, then the flow is essentially momentum conserving, and the electrons are going to flow like water does through a pipe. Now, in conventional metals, you're usually in this regime in which this diffusive length scale is the smallest one. So if you want to engineer this kind of flow, which is called hydrodynamic flow, in a metallic system, then the important thing is to get to this regime. And so how do you do that? So again, I apologize for the fact that this image seems to have covered some of the text. But the main thing is that you need a very, very clean sample, and so clean that the other length scale, which has to do with the amount, the length that the electron travels before colliding with impurities, is very, very large, because you have a very small density of impurities. So having an ultra clean sample is extremely important, so that this is the operative length scale. And synthesizing a sample like that was almost impossible till about a decade and a half ago, when people started making ultra clean samples of various two-dimensional materials, the most significant of which is graphene, which I guess many of you have heard of. And graphene is just basically a one atomic layer thick sheet of carbon atoms. So it's a pure single layer of carbon atoms. And it turns out that you can actually make this ultra clean, so clean that you can be in this regime. All right, fine. So the question is, how do we know if we are actually in this regime? What is the signature of this kind of flow? And it turns out that you can, in principle, even image the flow and see this velocity gradient that I showed you in one of my earlier slides. But a much more striking feature of this hydrodynamic flow in graphene is a violation of something called the Wiedemann-Franz law. So the Wiedemann-Franz law is a very important law when it comes to the transport of electrons in conventional metals. And what it is basically a relationship between the electrical conductivity, which features in Ohm's law, and the thermal conductivity, which features in heat transport in what's called Fourier's law. So these are these two transport coefficients. And the Wiedemann-Franz law tells you that the ratio between these two transport coefficients divided by temperature is a certain combination of fundamental constants, and that's what's observed in conventional metals. And so the import of this is that it essentially tells you that the carriers of heat and charge in a conventional metal are not only the same, but they're also scattered in the same way. So that, in some sense, is the physical content of this law, which is observed in most conventional metals. And it turns out that in graphene, when you're in this hydrodynamic regime, there's actually a very striking violation of the Wiedemann-Franz law. So you can measure this quantity, which my colleague Arindam Ghosh in the physics department has done in this paper. And you can compare it to what you would expect for a conventional metal. and you see that you can have a violation which is almost 3 orders of magnitude large. So this is a striking signature of the transport in the system not being of the conventional metallic type, and in fact actually being of the hydrodynamic type. And so you can ask, well, why does this happen? What is the essential physics? So to understand the essential physics, one has to realize that even though these electrons are moving in a very clean system, they're still moving in an environment of a certain sort, in a crystal environment. Now it turns out that if you want to think of the motion of these electrons, if you think of these electrons as particles which are moving, if they were moving in free space, and you wanted to think of them as classical particles, then they would just obey Newton's laws of motion. So these are just statements of Newton's laws of motion. And I have, in this second law, included a force which could come from an applied electric field. Remember that the electrons are charged, and also a force which could come from an applied magnetic field, which was the Lorentz force. Now it turns out that when you're looking at electrons moving through a crystalline material, right, because they're not moving in free space, there is a way in which these equations have to be modified. So the electrons are really not classical particles, they're quantum particles, they're waves. And so if you want to think of them as particles, you actually have to think of them as combinations or superpositions of waves, and the kinds of waves which are allowed to exist in a crystal, and these waves are what are called block waves. So the electrons, you have to think of the electrons when they're moving in a crystalline environment as particles which are made up of these block waves. And when you do that, it turns out that these equations have to be modified, and they are modified in a pretty interesting way, mainly this one. So you have a modification which looks like this. So instead of the velocity just being equal to the momentum divided by the mass, which is what you conventionally have in Newton's laws, you have something else here. You actually have this quantity, where E of P is what's called the dispersion, or in a certain sense is the allowed kinetic energy that the electron can have in this crystal as a function of its momentum, and that kinetic energy does not have to be equal to p squared by 2m. So this is what's called a dispersion relation, and it just comes basically from the fact that you have a crystal with a crystal structure. Then you also have the second term, which really has no analog here. This is something that's called an anomalous velocity. And so it's a velocity which depends on the rate of change of the momentum, and this other quantity here, which is called a Berry curvature. And this comes from the basic nature of these block waves. The form of these block waves actually gives you this Berry curvature. So there are these two very important modifications of the equation of motion of an electron when it flows through a crystal. And it turns out that the behavior that I showed you earlier can be explained because of this modification. So in graphene, the Berry curvature is equal to 0, so you don't need to worry about the second term. But you do have a dispersion which looks like this instead of p squared by 2m. And this is like the dispersion of a relativistic particle. And you can see that there's a plus and minus sign. So in some sense, you can have both a positive and a negative kinetic energy, which have to be interpreted as the energies of particles, electrons, and what are called holes, which are the analogs of, if you like, antiparticles in high energy physics. And so in the native state of graphene, you have neither any particles nor holes, and then when you increase the temperature, it turns out that you can actually get particles and holes. But again, in the native state of non-zero temperature, you have an equal number of them. They have opposite charges. And so then it turns out that when you apply a voltage gradient to set up an electrical current, the electrons and the holes move in opposite directions. And if momentum is conserved in the system, right, and these are moving in opposite directions and they are sort of completely symmetric, the total momentum is 0. And so if you switch off the electric field now, you can in principle degrade this current while keeping the total momentum equal to 0, because momentum has to be conserved, by degrading these individual currents, and so you can get a finite electrical conductivity. On the other hand, if you set up a temperature gradient to get a heat current, then it turns out that the electrons and holes have to move in the same direction. And now if you turn off the temperature gradient but the momentum has to be conserved, there really is no way of degrading this current. So in principle, you get an infinite thermal conductivity. Of course, in practice, that doesn't happen. Things are not infinite. but it's because the thermal conductivity and the electrical conductivity behave so differently that you have the spectacular violation of the Wiedemann-Franz law, which comes from a combination of momentum conservation and this funny energy momentum relationship in graphene. Okay, so I'll just conclude in the next couple of minutes. So another thing that I wanted to draw your attention to is the effect of the other term which I neglected, which doesn't exist in graphene, but it turns out that it can exist in other materials. And so in general, what happens is that if you have momentum conservation in a fluid, and you now look at how the electrical current and the heat current depend on gradients, then if you have momentum conservation, then there can also be a dependence on the velocity gradient of the fluid with an accompanying transport coefficient. And in addition to the electrical current and the heat current, you can also now have a momentum current which can be induced by gradients. So these are, so if you look at any standard textbook on solid state physics and you look at transport, these are the relations that you will see with these transport coefficients. But in the case of electron hydrodynamics, you have an extended set of relations with these additional transport coefficients, this one being a viscosity tensor. Okay. And so, and it turns out that these coefficients in magenta and blue are in some sense novel coefficients which haven't really been investigated before, called vortical coefficients. And the reason that they haven't been investigated before is that you actually need to break inversion symmetry. You need to have a situation in which when you invert coordinates about the origin, the system is actually different in a certain sense for these to be non-zero, and that is difficult to achieve in a conventional fluid. And so no one really talks about these coefficients. But it turns out that in an electron fluid, because of this particular term, you can actually achieve inversion symmetry. There's a way in which you can get inversion symmetry from the nature of these electron waves in certain crystalline environments. And that's represented by this Berry curvature term not being equal to itself when you invert the momentum. So in a situation like that, you can actually get these coefficients to be non-zero, these vortical coefficients to be non-zero. And this is something that we worked out. Okay, and a last thing that I want to say is that in this situation, in electron hydrodynamics, you can also, if you look at the momentum current or the stress tensor, it turns out that the stress tensor can actually be asymmetric, unlike in conventional fluids. And that asymmetry can be attributed to the fact that there can be an intrinsic angular momentum of these electron wave packets due to this Berry curvature. So an asymmetric stress tensor typically has to, tells you that the orbital angular momentum of the fluids is not conserved, and here that's because of this intrinsic angular momentum that these wave packets have. Anyway, so to summarize, I hope I've been able to convince you that electrons in certain funny kinds of metallic systems can flow like water through a pipe, and that happens when electron-electron scattering is the dominant mechanism and momentum is conserved in the bulk. There is an experimental signature, one among many experimental signatures, which is this large violation of the Wiedemann-Franz law. And in systems with a non-zero Berry curvature, you can actually get these novel transport coefficients to be non-zero, which you don't observe in conventional fluids. So thank you very much.
Thank you, Professor Mukerjee. Yeah, we have time for a few questions.
So my question was, when the momentum is conserved for this hydrodynamic regime, is there a practical relevance in which it changes the properties of that electron flow in the material? So will the material properties change? Is there a practical relevance for that material?
Yeah, well, so the thing is that the reason that the momentum is conserved is because of the material. It's because the material is so pure and that there aren't any impurities or any appreciable density of impurities for the electrons to scatter off, that the momentum of the electrons is conserved. It's not in some sense the other way around, that the momentum of the electrons being conserved is giving the material some properties. It's really more the properties of the material giving you this kind of behavior.
Ruth, I had a quick question. So of course, if it's ultra pure, you said that the heat transport is just infinite. I guess in the experiment, because you know the concentration of impurities, there's a simple way of estimating.
So eventually what makes your thermal conductivity finite and not infinite is the fact that you have some concentration of impurities, no matter how small that is, and also that sample has a finite size. So you do have this effect of the boundaries where momentum is sucked. So,
Is there any question? Yeah.
In the case of electrons, electron hydrodynamics, you have the quantum potential, right? Apart from the classical potential, the equation of motion, fluid dynamical equation should have a quantum force.
Okay, so you're asking what is the effect of the quantum potential or all of this? So the thing is, so I didn't tell you very much about where this dispersion is coming from. So the electrons are moving in a periodic potential, and that motion of the electrons in the periodic potential has to be considered as a completely quantum problem. And so the quantum mechanics of that problem is what is even giving you this epsilon p in the first place. So if you're thinking, if by quantum potential you mean the periodic potential considered and the quantum effects of that, so the most important place where that's going into all of this is in the form of epsilon of p. And this also, by the way, is a quantum quantity, because it comes, when I say the form of the block waves, it actually comes from the wave functions of the block waves. So that's also a completely quantum quantity.
Any other question? If there is no other question, please join me in thanking Professor Mukerjee for the nice lecture.